Hello, everybody. I hope you all had a good lunch. I'd like to thank the speakers for giving me the chance to share my work here. I'll be talking about the bulk of my thesis work, which is concentrated in sort of these three papers that came out over the last year and a bit. And I'll talk a little bit about, at the end, about some more recent work I've been doing. But what we're going to be doing is getting into the more nitty-gritty details of some of the spectra of FUors objects. To begin, you have already seen a couple of these plots. As we know by now, so I'm going to jump here. As we know by now, FUors objects have very diverse light curves. Recent light curves have continued to show that, but even in the original classical objects, this has been the case. And they show not only diversity in the original rises, where they can have either slow or fast rise times, but also totally different fall-offs. And the evolution after the peak of the initial outburst can tell us about what exactly is going on in the inner disk and hopefully help to constrain the accretion physics going on. The way we model these is based on the, as has been mentioned before, based on the kind of classic Shakura-Tsunayev viscous accretion disk that was modified to incorporate the inner region near the star. So you start out with this viscous disk that's transferring its gravitational potential energy to kinetic energy via viscous heating, and you get an accretion luminosity that totally dominates your system, right? So all you're seeing really is the disk. From these basic assumptions, you can put together a temperature profile that just looks like this. It, as Lee showed earlier, T max generally falls off as r to the minus 3/4 if you push things around here. But what you'll find is that you don't, in the original model, of course, there's an assumed black hole there, so the temperature should go to 0 as you approach the central source. We, of course, know there's a star there, not a black hole, so you're going to get some excess heating. This has been traditionally treated as just an isothermal treatment interior to the maximum temperature of the disk. And to tease a little bit of what I'll talk about near the end of my talk, we actually have recent observations that do support the fact that, how do I make this light up? That do support this kind of isothermal little bit interior to in the last few tenths of the disk, and that actually does make a difference to your spectra. Observationally, this temperature profile produces a mixed spectral type, as again Lee talked about earlier, that's been known for a while. But I just want to highlight a couple of details here because the mixed spectral type is known to vary from, as you look here in the even red optical to the near IR, but also if you go from the blue optical to the red optical, you see the spectrum is consistent with earlier types on the bluer side and later types on the redder side. But we also see in the red optical absorption from very hot features. So it's not strictly the case that if you take a snippet of continuum at 4,000 angstroms and a snippet of continuum at 8,000 angstroms, you're tracing totally different parts of the disk. While that's true in general for the continuum emission, the absorption lines that you're seeing are still dependent on what the actual excitation potential of the line is. So in all that to say, when you look in the red optical, you can still see absorption lines that are consistent with very hot atmospheres, in addition to the classic, cooler molecular absorption that you see and lower excitation potential atomic lines. When we model them, we have to take into account all of these parameters. So you have the basic ones that you've seen already in the temperature profile, the stellar mass, the mass accretion rate, and the inner radius or truncation radius of the disk. But you also have to consider where you're actually cutting off your model on the outer disk part, what the disk inclination is, of course, the extinction to the source, and your distance if you're doing everything fully. A lot of these are degenerate. When we look at just the SED, strictly comparing a couple of these parameters as an example, for if you just take one model and you vary individual parameters, you can immediately see that the extinction and the inner and the truncation radius are quite degenerate with one another. This is because extinction actually trades off with the temperature, the max temperature in the disk, and the inner truncation radius strongly impacts that. The mass accretion rate more generally affects the overall SED because it's the accretion luminosity goes linearly with it. And you see that that becomes a little bit degenerate with the actual inclination that you're observing, or in general, the overall luminosity can be degenerate with the distance to the source as well. All that to say, SEDs alone are not quite enough. You really need to look into the details of the high-resolution spectra. You can do this by taking it, and this allows you to then take advantage of the fact that you assume the gas is in Keplerian rotation. The Keplerian broadening then actually combines your mass and your truncation radius and allows you to constrain the mass of the central object independently of the typically used m dot factor that you can otherwise otherwise SEDs only constrain as a product. When you look at the high resolution spectra, the actual models that we're using have different parameters impact the absorption lines differently. Most importantly, you'll notice that the assumed inclination can have a really radical effect on the absorption line, not just the absorption line width, but of course the actual presence of certain lines. So the actual ability to detect certain lines for different signal or noise levels of the spectrum, and the mass accretion rate and inner truncation radius have slightly different impacts on the line broadening as well. And this is stuff that I discuss in detail in my 2023 spectroscopy paper of V960MON if you're interested in seeing a little bit more about that. But when we have this model, we can use the data to kind of construct this picture of the FUors accretion disk. So this is sort of a cartoon that combines some of the information from Zhao Anju's simulation that from 2020 that Lee showed earlier, as well as data from the HPC 722 system that we published earlier this year. The truncation, again, the truncation of the disk is essentially right at the surface of the star. For this particular system, we find it to not be exactly the surface of the star. We have a constraint on the radius of the star from a pre-outburst spectrum that indicates it's actually a little bit smaller than what we find to be the best fit truncation radius, but there could be some wiggle room there. In general, we find the maximum temperature of these disks is about 6,000 to 8,000 Kelvin, as has been mentioned before. And in our models, we truncate them approximately where the disk atmosphere would you would need to start incorporating dust into the model. And at that point, we find that the data are consistent with there being then a passive disk that's just reprocessing the emission. Our models are excellent fits to both the high resolution spectra and the SED. And what we actually do is we fit the SED, and then you can essentially just zoom in on the model and get the high resolution spectrum from exactly the same parameters and exactly the same modeling setup, just a difference in resolution. So the nice thing there is that you can simultaneously use the constraints from your high resolution spectra to constrain your SED, and that gives you a more consistent fit with finding system parameters that join those two together. So we can then use that to actually study the very detailed spectroscopic evolution of two systems. I'm going to talk about two systems that you've heard a little bit about today, or you'll hear about V960MON later this week, but you heard a little bit about HPC 722 earlier today. V960MON went into this very sharp rise and then this kind of exponential fade. It sort of looks like the V1057 SIG system, but with like a fading time about 10 times faster. And what we looked at is the spectroscopic evolution of the system during this kind of exponential fade time. Again, sorry, using our modeling, we were able to constrain kind of a uniform picture, a unified picture of the system, where we have our disk atmosphere with a peak temperature of about 8,000 Kelvin at the peak of the outburst, and we see evidence of wind outflows. But mostly in the dynamics of the disk, we see that as the disk is in this exponential fade, the magnetosphere seems to be reestablishing itself. So so of course, if you assume that the truncation radius is this balance between the magnetic field and the magnetic field energy density and the Ram pressure of the accretion, you end up with a description of its dependence on the accretion rate of the system. If we start out assuming that it's essentially right at the stellar surface, and you allow the accretion rate to then modulate the inner radius so that it does move out, we find excellent match to the spectroscopic and photometric evolution of the system. and indicates that the inner truncation radius has moved out during that exponential fade over about 2 years by about 0.4 solar radii. This seems really tiny, but it leads to an enormous change in that huge change in the brightness of the system, and is consistent with this evolving on the viscous timescale, assuming alpha values consistent with the MRI instability. As I mentioned, our models are an excellent match to the spectroscopic evolution, with the exception of some excess absorption due to usually what we attribute to outflows in the system. Looking at HPC 722, again, there was an enormous burst followed by a pretty intense fade that's not quite like the V960 Mon 1. It was a little bit faster and doesn't have that kind of exponential shape, but then the system kind of turned back on. So I'm going to call these the peak, the dip, and the outburst, the dip, and the plateau. This system we find seems a little bit more complex. It has clear evidence, at least during the dip, of a very strong fast outflow, but otherwise we still see this rotating disk wind, and it's a little bit cooler. It's only at about 6,000 Kelvin at the innermost region. In this system, we don't see evidence of the inner truncation radius moving around, but rather our outer, where the viscous disk transitions into being the more passive. We go from the viscous disk out to the more passively irradiated disk, and we see that. So in 2010, at the peak of the burst, it had about a 25 solar radii cutoff. In 2011, it was about 35, and by 2015, it had moved out to 100 solar radii, or about a half AU. This is again consistent with evolution at the viscous timescale for alphas of about 0.1 in the system. And it seems to be indicating that for this outburst, there's some kind of a maybe combustion front or something, where it's kind of propagating outward and turning on out further radii. The way you're actually able to see this is in the SED, and we get that, you know, the 2 to 5 micron region is sensitive to exactly what this R outer parameter is. For larger values, it's of course brighter, and we get an excellent match. Sorry, the colors aren't showing up great, but we get, but you can check this figure out in my earlier paper. But we get an excellent match to the data by assuming that at outburst, again, that R outer is set at 25 stellar radii, and you have a passive disk component picking up the 3 to 5 micron range. Later in the dip, you need a little bit less of the passive disk as that outer truncation is moved out a little more. The outer radius is moved out more. And by 2015, you actually don't have any contribution by a passive disk in this wavelength range. It's entirely explained by our viscous disk model. It's also an excellent match to the evolution of the high-res spectra in that time, as well as the near-spec spectrum that we took in 2023. So these models are able to explain both the visible high-resolution spectra at about 5,000 angstroms all the way out to the 2.5 micron range, with very few outliers, most of which can be explained by outflow absorption in the system. So speaking of outflows real quick, both of these systems show enormously massive winds, mostly that are these very low velocity flows out to maybe, not very low velocity, but low velocity flows out to about 30 kilometers per second, maybe out to 50 in V960 Mon. But they are highly variable over the evolution of the light curve, especially in H alpha. And the H alpha emission we find to be consistent with models for relatively warm winds, so indicating that these winds are indeed maybe 4,000 to 6,000 Kelvin, which are, so we encourage modeling of FUors winds as warm winds rather than the typically previously done cold wind models to try and explain this, the emission that you see both in H alpha and in the calcium infrared triplet. I want to call attention to this strange narrow blue shifted absorption that appears both in HPC 722 and V960 Mon. In HPC 722, we found it not only across the entire visible range, but also in the near infrared with our high-res spectra, with our near-spec spectra, and we find that this seems consistent with a relatively high opacity disk wind that comes from that the upper atmosphere of the disk, as Lee was indicating, is right where the wind is actually being launched. So it might be high density, and that would explain why you're able to see it in all these weaker lines that typically only trace disk emission. I'm going to skip this for now. As I mentioned earlier, we have recent data from HST where we actually detect FUV continuum excess in FUORI. So we're able to actually get down to that region of the last few tenths of the disk, and we find that the viscous disk model, which is shown here in this kind of light blue, compared with the data in the background in the darker blue, the viscous disk model does an excellent job of matching the continuum all the way down to about 2,400 angstroms, at which point, once you reach the FUV, you need an excess component. But this viscous disk model is that using the isothermal last few tenths of a stellar radius. So you really can't test it much better than that, and we're finding really good consistency with that relatively simple model. So it seems to work. We don't quite know what this excess is. We find that it's consistent with being a shock right at the star disk boundary, but we model it with a relatively simple black body model and find that it's a 16,000 Kelvin component with a very, very small filling factor of about 10 to the minus 4 of the stellar surface. But again, we think it's consistent with the surface accretion layer that's proposed in Zhao Anju's 2020 simulation, then shocking onto the stellar surface and producing this emission. I'll leave my summary up here and open to questions.
Oh, thank you very much for the very nice talk. Just a magnetosphere thing for V960 MON. And okay, you say so. Still, a magnetosphere still affects the results, but the still boundary layer mass accretion occurs, not magnetospheric mass accretion. Is that your point?
Yeah. So this is we're saying the magnetosphere may be reestablishing itself, so we still believe that it has been crushed by the outburst, or there might be some sliver of space between the inner disk and the stellar surface. But the evolution at least is consistent with the magnetic energy density pushing back out again as the accretion rate decreases. So these might be the early stages of the magnetosphere reestablishing itself.
Hi. So my small question is, you mentioned that your model is very good, except for in a few cases in which the lines do not really match. Have you tried adding more components? Maybe each species is at a different inclination or something, or maybe this is just overfitting. I don't know what it would be.
Yeah, so our model uses just the existing grids of stellar atmospheres, like Phoenix grid or BT settle. And so we're using the kind of pre-cooked stellar spectra. I would argue that you can probably do even better pretty immediately just by doing a very careful job, spending like a few months putting together a set of templates that span the entire range of temperatures and gravities that we're using. Just because there are known inconsistencies between some of the absorption lines in these. But because we don't treat each line individually in our model, we aren't able to do that. But that's certainly something that should be considered for sure.
Question here. Yeah, so very interesting. But can you somehow put constraints on the geometrical thickness of a disk from your modeling? Because for such large accretion rates, the theory predicts that the disks could actually be quite geometrically thick. So, with H upon R 0.3 or so, can you exclude that from your modeling or confirm it?
From our modeling, I don't believe so. But what we are finding is that, again, the thin disk model does do a really great job. The caveat here is that what we are looking at when we do the thin disk model is still that disk atmosphere, right? We're looking at tau equals 1. which as Lee showed, and as your work has shown also, the midplane is way hotter than that, right? And then there's this plane parallel atmosphere above that hot midplane. So what we are saying is essentially that nice plane parallel atmosphere that forms above the very hot midplane still looks like, observationally, the thin disk. But no, I don't think we can necessarily constrain that, but I'd love to chat about how we might.
Okay, thanks.
Okay, so thank you for a super nice talk. And this question is a little bit related to the other one we just had, because I was wondering in these objects with very high accretion rates, right? There's a question about how does the boundary layer, how big is the boundary layer? Does it engulf the star completely, or does it only become a spot on close to the equator? And I was wondering if your models can say something about this, because this is also important for, say, the very early protostellar evolution.
Yeah, our model, the best we could do with the boundary layer is to try and look kinematically at the effect of the boundary layer. So you would vary the rotation from, it would become, become strongly subcaplarian as you approach the stellar surface, assuming it's shear heated, and that's so you would actually be able to see it in the kinematics. But it seems like so we are not really seeing that. I've attempted to do that in a couple of our models, and the spectral lines don't quite match. You end up with a much deeper core to the line than what we see. The other thing is that, I think that detailed modeling of, in particular, this, and figuring out what exactly is producing the FUV, if it is indeed a shock like what we might be proposing, the actual geometry of the shock and what is along the line of sight between us and it could tell us about whether there's a boundary there, and then it's shocking onto the surface, and how much it might be engulfing the surface of the star. But right now, there doesn't seem to be much indication of a boundary layer as it has been proposed in theory in the past.
Okay, I would like to hear some questions from early career scientists. Please, students, I would like to hear your questions. There are no stupid questions at conferences, okay? So I'm going to leave the microphone to Lee Hartman, and then I would like to hear some of these questions.
Me too. Just in terms of that expansion, right? That seemed awfully fast. That's much faster than a viscous time scale, right?
I was doing, so this is...
Because, the viscous time scale is like the orbital period divided by alpha and multiplied by r over h squared, right? So that might be more like, so I don't know, maybe I'm doing it wrong, but it seems to me like it would be more like a thermal front or something.
Yeah, it may certainly be. I think I might have been generous with some of what I was assuming when I was doing the back of the envelope math there, and I think it's something. So what it is it's a couple of orders of magnitude slower than the dynamic time, and like within an order of magnitude of the viscous time. But it's not. It's somewhere in it's maybe faster than the viscous time, but somewhere around it, depending on what you assume for h over r and what are you allowed alpha 0.1 or 0.4? That'll give you a factor of a couple, and right. So that was sort of there. It was close enough to wiggle room that I felt okay saying it. But it is a little faster than the viscous time.
Okay, time for a last question. Students' question? No? Antonio.
I'll try to encourage our younger attendants by doing a stupid question. You mentioned mass as a variable in your models. Were you fitting for mass in these models, or were you using previous measures of the stellar mass?
So in the two systems, we did it a little differently. In V960 Mon, we didn't have a strong prior on the mass. We had a little bit to inform it. And so we did allow it to be a variable in our fit. In HPC 722, because we had the progenitor spectrum, we estimated the mass based on that, and then fixed that, because there were some other, for instance, the inclination to the system wasn't. So in V960 Mon, we had a good prior on the inclination to the system. So you sort of have to play around with what you can constrain. So, so in V960 Mon, we allowed it to vary. In HPC 722, we fixed it.
I was just wondering whether you could use some ALMA data in which people have fitted for the stellar mass using CO rotation curves and see how those could affect the results.
Yes,
instance,
absolutely. So we're
V883 ORI has a very good estimate from Lucas' 2016 paper.
Yeah, precisely. That's actually one system where I am working toward doing one of these models with it, and we are in fact taking advantage of that because those masses are rare, and in fact, so Agnes's work on helped to constrain the inclination for the V960 Mon system, but a lot of our sample is biased toward the northern hemisphere because it's what Keck can look at. And so there's some overlap between the Keck and ALMA targets, but most of our sample is not accessible to ALMA. Or not most, but a good fraction.
Okay, let's thank the speaker again. Thank you very much. And our next speaker